So looking at this polynomial, x to the fourth plus 2x cubed minus 5x squared minus 2. How many zeros should it have? How many zeros should that polynomial have? This one right. Or you can think of it as factor or x. How many should it have? 4. Yes, 4. There are a maximum number of 4 zeros possible for this polynomial. So I'm going to say 4 because the degree of the poly is 4. Meaning the highest exponent is a 4. That's the degree of the polynomial. All right. However, when we go to graph this, I go into white. Oh, look, I already have nice. How many zeros, how many real zeros do you see? 2, right? There's one that's between 3 and 4, and there's one that's between 1 and 2. So here, there are 2 real zeros. So what does this mean? There should be 4, right? That's the degree of the polynomial, but there's only 2. What does that mean? Yes, there are 2 imaginary. And the way that we know that there are more zeros than the real zeros is because the changes in direction there below the x-axis. You see how it goes down and then comes back up and then has a maximum point still below the x-axis? And then it goes down and then comes back up. All of that shape of the polynomial needs to be formed somehow. If we didn't have those imaginary zeros, this would have just been a problem, right? All of this middle, all of this middle stuff in the middle would have been gone and it would have just gone down and then back up. So there has to be 2 what are called imaginary zeros or complex zeros. And these zeros can be theoretically found at the turning point. The reason why I say theoretically is because if I say they can be found at the turning points, you guys are going to try to go in and find the x value there to find the 0. But you can't do that because they're imaginary. They really don't exist. But we know that something needs to be there. So they found at turning points of graph. That's how we know that there are imaginary roots, because we have turning points that don't force the polynomial back to the x-axis. Okay, so I'm just going to sketch this so we can reference it later, or you can reference it later. These are the real zeros. These are the complex zeros. If they hadn't done that, there wouldn't have been a turning point. Oh my God. And this would have just been a quadratic. All right. So then a couple of things before we go and try to find our complex zeros. Whenever we're given a complex zero, or the problem tells us there's a complex zero, say it tells us that there's a zero at a plus bi. Complex zeros always have what are called conjugates, meaning not only do we have a zero at a plus bi, we also must have a zero at the conjugate a minus bi. So all we did was take the addition between and change it to subtraction. These are called conjugates. There's always a pair, a plus or minus of imaginary zeros. Always, always, always. If we think of the quadratic formula, remember in front of the square root, there's a plus or minus. Always, right? Meaning you are always going to have the opposite version of the imaginary zero as well. So let's see what that really means here. Given one complex zero of f of x, state its conjugate and the two factors. So here we have x plus 3i, x equals 3i. Because we know that 3i is a complex zero, what else do we know is a complex zero for this problem? Mm, yes, minus 3i. Minus 3i. This complex zero is like the bi part of these formulas, right? There is no a in this example. So we just change this from a positive 3i to a minus 3i, meaning that our factors for these zeros are x minus, whoops, x minus 3i as well as x plus 3i. Oh, yeah. Now over here is the trickier one, just because now there is an a, right? So we have an a plus a bi, 2 plus 4i. Because this is a complex zero for this problem, what else do we know is a complex zero? Yes, thank you so much, B. Notice we are not changing the sign of the 2. You are just changing the sign between the a and the b value. So it becomes 2 minus 4i. That being said, what are my factors? That being said, what are my factors given these two complex? How do we change in general? Okay, so example, how do we change this zero into, what do we do to it? Oh, Andrew, I mean, Ruby, yes, you got it exactly. Yes. Let's see, did other people get it? All right. Arnon, yes, you subtract the 2 over and it becomes x minus 2. Same exact concept. You are subtracting both of the terms over. So for our first complex zero, it becomes x minus 2 minus 4i. And then this one still has an x minus 2 because we're still subtracting the 2 over, but then it's plus 4i. So notice it is negative 2 no matter which complex zero you're dealing with. That's the tricky part about this concept. Only the symbol between the a and the b value changes. Does that make sense? I hope. Okay. If not, we're going to practice it. Wait, And when you square them, exactly. So I'm glad you pointed that out, Ruby. Here. If I look, where do I want to put this? Remember, what does I represent? Yeah, that's it. What does just plain I represent? Exactly. We needed something to replace the square root of -1 because you cannot square root a negative number. It's impossible. However, we needed to come up with a placeholder so that we could continue doing our problem so that eventually maybe the I would disappear. All right. We needed to come up with a placeholder so that we could keep doing higher level math and we wouldn't have to stop the problem. We could just keep going in hopes that eventually the I's would go away. And the I's go away if they are squared, or actually if they're raised to any even power. Math is so weird, right? I say this to all my students whenever they ask what actually do the magic numbers. I is used all the time in the real world, all the time. We wouldn't have GPS if not for imaginary numbers. We wouldn't have most technologies if not for imaginary numbers. Because if we didn't have that, hold on to that imaginary number, we would have all of these complex problems and we would never come to a solution. Okay, like Ruby was saying right here, I squared is just -1. Because when you take the square root of -1 times the square root of -1, you're left with just -1. Anytime you multiply a square root times itself, it's just the number inside. So that's how we get rid of imaginary numbers. Okay, so let's go ahead and try to apply this. Write a polynomial function f of x in standard form, given the key characteristics of the function below. So number one says a degree of 3. So we know that this is a cubic function because it has a degree of 3 with zeros 2 and 3i. So this first one gives us a factor of x minus 2. What does 3i tell us? What factor can I write down for vector, I should say, because it actually gives us 2. What two factors does 3i give us? Yes, exactly. X plus 3i. Well, I should write down the one it gave us first. So this 3i gives us negative x minus 3i, but it also gives us the conjugate x plus 3i. There's always a pair of complex, always, always. So now we have to multiply. We have to multiply everything here to get back to the original polygon, or oh my gosh, polynomial in standard form. Does anyone know which two factors I would multiply together first to make my life easier? Yes, you would multiply the complex zeros, the complex factors first. Why? What do you notice those complex factors are? Hmm, you're right, the eyes will cancel. However, if I had instead replaced those factors with this, what do you notice this is an example of? Oh, not sum squares, difference squares. Oh my God, difference squares pops up again. So we know that if these are our factors, our original quadratic is just the square version of all of these terms. So I write first, what is x squared? It's x squared. What is 3i squared? What should I write? I don't think sum of squares exists. It kind of is, and we'll go over that in a second. Right. Uh, exactly. You have to square the 3 as well. So it becomes 9i squared, and it's a difference of squares, so there's a minus between them. Now, what further can I do here to my quadratic just to simplify it? Yes. Remember, we just went over I squared is equivalent to -1. So this becomes x squared plus 9. Exactly. Oh, Andrew, Ruby, I see exactly why you previously said sum of squares now. Yes. Because technically this is right now sum of squares. Yeah, sum of squares. All right. So here I now need to multiply these together. I'm going to distribute everything, double distribute, and end up with x cubed plus 9x minus 2x squared minus 18. But then I'm just going to finish this off writing it in complete standard form because right now I'm not in order. I'm out of order with my exponents, so I'm just going to turn them around to have it x cubed minus 2x squared plus 9x minus 18. This is my polynomial in standard form. Any questions on this? So this polynomial, x cubed minus 2x squared plus 9x minus 18, has one real root and two imaginary roots. Meaning, I mean, I don't really know where it is on the graph, but if I was to go ahead and graph this would be something like that, right? It has it has more turning points, but it only affects the same time. This is a pure guess about what this looks like. This could be up here. I don't know. I have no idea what it is. All right, so let's go ahead and we're just going to set up number 2. We're going to set it up, and we're also going to set up number 3. We're not going to solve them. We're not going to finish solving them. It is shifted to the right more and very steep. Yeah, I assumed it was a huge gap. All right. So here, this is the degree 5. So this is actually a much larger problem with zeros 1, 6, -3, and 2 plus I. How would I write the factors if my complex 0 is 2 plus I? Yes, exactly, Mario. Here we have x. Remember, we're subtracting everything over, so it becomes a -2 minus I. But we also have the conjugate, x still -2, but now a plus I. Yeah, yeah. You have it all ready to go. You're like, I know she's going to ask this. Here we go. I'm going to pre-type it. Press enter. All right. It is. I'm not going to show you how to multiply the first real zeros together. You just have to distribute a whole bunch. But I do want to show you how to multiply the imaginary zeros together. Now, I know that previous or your old teachers may have substitute something in for x minus 2 and then distribute and then square the x minus 2. I honestly enjoy distributing, just plain distribution. So that's what I'm going to do. Again, if you know another way to do this, if you want to do it with the box, if you want to use substitution, go for it. But this is just how I was taught. This is how I like it. So this is how I'm doing it. So I'm going to multiply x times negative 2, x times I. So I get x squared minus 2x plus xi. Then I distribute the negative 2. Negative 2 times x, negative 2 times negative 2, negative 2 times I. And then lastly, I multiply negative I times x, negative I times negative 2, negative I times I. Now, anytime you're multiplying conjugates together, if you're doing things correctly, all of the i's should disappear. All of the i's disappear, right? Because these i's were created by real numbers. They were created by real numbers. You should not have an I when you're multiplying conjugates. So everything should cancel here. We have a negative xi and a positive xi. Those cancel. We have a positive 2i and a negative 2i. Those cancel. What else goes away here? Right. Yes. This I squared becomes a negative 1, meaning in total, what does this end term represent? Okay. Yeah, a positive 1. So in total, we have x squared, the negative 2x and the negative 2x become a negative 4x, and then we have plus 4 plus 1, which becomes plus 4. So this whole thing was created from the quadratic x squared minus 4x plus 5. And then you would have to distribute everything else. I'm not going to do that. It's simple yet tedious. We don't have time for it. Let's see. So I'm just going to write so you know not. Any questions here? I don't believe that we are ever going to make you find the polynomial side, okay? It's just a lot of work. All right. And then on this one, this number 3, I just wanted to go over it really quickly. I think that you could understand on your own, but just in case, I do want to state that if we have a 0 that has a multiplicity of 2, what does this mean for this 0? Yes. Anytime we have a multiplicity of 2, that multiplicity is the exponent of the factor. So if the 0, 3 has a multiplicity of 2, it means x minus 3 is actually squared. Right, there are 2 of them. It means that this is a, oh, this one, what could you imagine this one looking like? Mm-hmm, mm-hmm, mm. Well, it's at a positive 3. I would imagine this looks something like that, right? Um, it's it's of degree 4, meaning it's even. It's not negative, so it goes up in both directions, and it immediately bounces off of the 3. Do you need to know this one? Right? I like imagine polynomials. All right. Any questions on finding the polynomial given one of the or given all of the roots? Okay. So now what we need to do is we need to go over